Hi, welcome back. So for today's video, we will be discussing electric circuits, introduction to electric circuits and network theorems. Okay, so we have already discussed series and parallel circuits and the combination of series and parallel circuits wherein we can solve different parameters like currents, voltages, and resistances or even power with simply the use of Ohm's law. Okay, so we also discussed the delta to y and y to delta transformation, which will be very helpful for us to solve for equivalent resistances in a very in a circuit where it is difficult to analyze whether the resistance combinations are in series or are in parallel. Okay, however, class, there are electric circuits that are somewhat still difficult to solve due to larger amounts we can have or we can even solve them, but it will give us it will need for us to have many equations before we can even solve it. Okay, so therefore we will start to discuss new techniques or new network theorems that can help us. Okay, so aside from Ohm's law, okay, so we will be adding some techniques or some other theorems that can help us. So this theorems is are not made for our lives to become difficult, but rather to ease our computations. Okay, so but before we go to that, we will be discussing few definitions, okay, so that we can understand more our succeeding discussions. Okay, so to start with, we have this following definitions. Okay, so first is of course a circuit. So what do we mean by circuit? So this is a closed conducting path. Okay, so through which an electric current either flows or it is intended to flow. Okay, so from now on, we will be analyzing different types of circuits. So we will be although for now, we will just consider resistors, but at the latter part of our discussion, we're going to try other circuit components, okay, like capacitors and inductors. And if we still have time, maybe we can even start with non-linear components. Okay, then we have here parameters. These are various elements of an electric circuit like resistance, inductance, and capacitance. Okay, so it is either lumped or distributed. So when we say lumped in a certain connection, this is a combination of the RL and C parameters, like you have resistors combined with capacitors or inductors, or distributed, so resistors only, capacitors only, or inductors only. Okay, and then we have here linear circuits, one whose parameters are constant. Okay, so the first part, or the first part of our discussion, we will be concentrating on linear circuits. So these are cases wherein our what do you call this, the relationships of our voltage, currents, and resistances are linear, or they are directly proportional or indirectly proportional with each other. Okay, so they do not change. Okay, so they do not change with the values of some specific parameters in a circuit. Okay, then we have here linear circuits, we also have non-linear circuits. However, maybe we will have a low concentration on this topic. Okay, so these are parameters that change with voltage and current. So we have here bilateral circuits. Properties or characteristics are the same in either direction. So usually good example for bilateral circuits are transmission lines. Or we have unilateral circuits. This has a properties or characteristics which change with the direction of its operation. Okay, so some examples of unilateral, for examples, are diode. Okay, so diode rectifiers, for example, it cannot perform rectification in both directions. So it's either in a forward mode or in a reverse mode only. Okay, and then we have electric network, wherein this is a combination of various electric elements connected in any manner whatsoever. Okay, so usually the thing that we're going to analyze are usually electric network, because it combines several parameters. Okay, so there are two types of network. We have the passive and the active network. Passive network contains no source of EMF in it, or electromotive force in it. And then active network contains one or more than one source of EMF. Okay, so unless stated, electric network should be assumed to be passive. So the resistors, the capacitors, and the inductors that we are using are usually passive. Okay, they are passive components. At the end of the subject, if we still have time, maybe we can discuss some active components like diodes, like transistors. But in the meantime, we're going to assume that we're going to make use of passive components first. Okay, so we have a node. So what do we mean by a node? So this is a junction in a circuit where two or more circuit elements are connected together. So from our previous videos, for example, we have point A in a delta connection. So wherein your R1 and 2, or your R3 and 1, for example, is connected. So we term that as a node. Okay, so we didn't define that as a node yet, but this time let's give that a name, that point a name, and that we will be calling that as a node. Okay, then we have here branch. Okay, so what do we mean by a branch? So this is a part of the network which lies between two junctions. Okay, so usually where the resistor is being located, we call that as a branch. Okay, and then we have a loop. Okay, so we have a loop. This is a closed path in a circuit in which no element or node is encountered more than once. So you're going to go around a certain loop only once. Okay, so the current that will be passing that certain path is it will pass only a certain path only once. And then we have a mesh. Okay, so it is a loop that contains no other loop within it. Okay, so as we go on with our discussion, we will be again encountering this term. So for now, I'm just wanting to define this for you, and then later on we will be elaborating on some of the different definitions. Okay, so various theorems will also be discussed, and we will be using those theorems in solving more complicated networks. Okay, so we have here an example. Okay, so we have here an example for A and B. Okay, so for letter A, for example, we have there 7 branches. Okay, so where are those 7 branches there? So we have here 1, 2, 3, 4, 5, 6, and 7. So we have 7 branches. This is where your 2 nodes are connected. So 1, 2, 3, 4, 5, 6, and 7. And then we have 6 nodes. Okay, so 2 points connecting 2 points. So where are our 6 nodes there? So you have 1, 2, 3, 4, 5, and 6. So those are your 6 nodes. Okay, and then we have 3 loops. Okay, so where are our 3 loops? Loop number 1 here, loop number 2 here, and then the big outside loop. Okay, so we have 3 loops, and we have 2 meshes. Okay, so where are our meshes here? 1 and 2. So we will not consider the outer loop as a mesh, because the mesh is defined as a loop with no other loop within it. Okay? If we consider the outer loop, there are two smaller loops inside that. So, therefore, it is considered as a loop but not a mesh. Okay? But a mesh, we can consider it as a loop. Okay, going to our letter B example here, how many branches do we have? Okay, so if you're thinking that we will be counting the following as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. So we do not call that as a branch. Okay, ma'am, how about this one? It has no element, but yet it is considered a branch because we have here two nodes, node 5 and node 6. However, in this example class, we only have two nodes. Okay? So, what are the two nodes here? So, we can consider this darken point here as your first node and the second node here. Actually, this whole, okay, this whole upper portion here is considered as one node because there are no other elements connected, okay? Just the L, the C, the R, and the V. So we consider this as one node, and we can also consider this as one node. Therefore, we cannot consider each of these lines here as a branch. Okay? Therefore, in this case, we only have four branches. So, where are your four branches here? You have 1, 2, 3, and 4. And then we have two nodes, 1 and 2. Okay? Now, how many loops do we have? Okay? So, we have 1, 2, 3. We have 4. We can have here 5. And then we can have here again 6. So, we have 6 loops. But we only have 3 meshes. Okay? So, where are the 3 meshes located? So, this is 1, 2, and 3. You have 3 meshes there. Okay? So, that is the definitions, or that is how we analyze node, branches, mesh, and loops. Okay? So, we're going to need that in the future discussions that we will be having. Okay. So, we have here approaches of network, excuse me, of network analysis. Okay, so we have what we call direct method. So what do we mean by direct method? This is a network, the network is left in its original form, okay, while determining different voltages and currents. We're going to try to solve that certain network, but we will not try to change or alter the physical appearance of that circuit. So we call that as the direct method. We will just get equations. We will try to formulate equations coming from that circuit without changing the physical appearance of your method. So that is direct method. So we will be discussing different approaches, different network analysis using the direct method. So to give you some examples, we will be having the Kirchhoff's laws. Okay, so we will be having the Kirchhoff's current law and the Kirchhoff's voltage law, and then we will be having what we call the mesh analysis. We will be having the nodal analysis, and we will be having the superposition method. Okay, so those are four examples of direct method. And then we have the network reduction method. So in the network reduction method, okay, as being differentiated from the direct method, so the original network is converted in a much simpler circuit for rapid calculation of different quantities. So therefore, since we're going to convert a complicated one to a more simpler one, there will be a change in your original circuit. So there will be an alteration, and that is what we call the network reduction method. Okay, so some examples of network reduction method is the one we have already discussed previously, the delta to Y conversion, because technically there is a change in the circuit, right? So from delta, we change that into Y and vice versa. So that is one good example of a network reduction. Okay, another examples of network reduction that we will be encountering throughout our discussions are the Thevenin's theorem, or the Norton's theorem. So those are some examples wherein we are going to alter, or we're going to change the original picture, or the original circuit that we are trying to solve, to not to make it difficult or not too complicated, but rather to make it easier to analyze. Okay? So, let's go to the first method. Okay, so this is under the direct method. Okay, so this is under the direct method, and we call this Kirchhoff's laws. So these are Kirchhoff's laws. So we have an S because technically we're going to make use of two Kirchhoff's laws. Okay, so what are those two? I think you're already familiar with some of them. Okay, so this was named after Gustav Kirchhoff. So some other pronunciation, I think it's some call this Kirchhoff. Okay, Kirchhoff's laws. Or some other calls this Kirchhoff's. So I just pronounce it as Kirchhoff's because when I was still in college, my professors usually pronounce it as Kirchhoff. So uh, follow their pronunciations. But other than that, I am hearing other pronunciations like Kirchhoff's. Okay, so it's up to you if you wanted to watch other videos. To have a supplementary knowledge about this one, so it's up to you anyway. What is important is you know how to make use of these laws. Okay, so we have here two laws. Okay, so these laws are more comprehensive than the Ohm's law. So what we are aware as of now is the Ohm's law, and we're trying to make use of the Ohm's law in our series and parallel circuits. Okay, so for now we're going to add so we will not forget about Ohm's law. Ohm's law will always be Ohm's law. We will always use that, but we will just add more, okay, laws to have us an easier way to compute circuit analysis problems. So these are laws that are more comprehensive than Ohm's law and are used for solving electrical networks which may not be readily solved by the latter or by Ohm's law. This is particularly useful in determining the equivalent resistance of complicated networks of conductors. Okay, this is useful in calculating the currents flowing in the various conductors. So we have here the first law. We call this as the Kirchhoff's point law, or the Kirchhoff's current law, or simply as KCL. Okay, Kirchhoff's current law. It says here, in any electrical network, the algebraic sum of currents meeting at a point or a junction or a node is equal to 0. So to be very simple about that, we're going to assume that all currents entering a specific node is just equal to the currents leaving that specific node. Okay, so that will give us a formula wherein we have summation of current is equal to 0. Okay, so the total current leaving a junction is equal to the current entering that junction. No accumulation of charge at the junction. So, hindi sila pwede mag-stack. Hindi pwede, o sige, 5 yung dumating, apat lang yung aalis. Okay, so yung isa maiwan. So, hindi pwedeng ganun. So, lahat ng mag-enter sa junction must have to leave that specific junction. Okay? And then, we will make some assumptions. Okay? So, we will make an assumption that all incoming currents are positive and all outgoing currents will be negative. Actually, there's no specific rule that all incoming currents are positive and all outgoing currents are negative. So, we cannot find any rule like that. So, all of those are just assumption. So, it's okay if you assign negative currents to incoming but you have to assign positive to outgoing. As long as there's a positive and there's a negative, it is not a problem. Okay? So, just for uniformity, just for uniformity, I guess, so we can say that, let us just assume that incoming currents are positive and outgoing currents are negative. Okay? So just like in this case, for example, considering our point A here, okay, so what are the currents entering point A? So currents entering point A are I1, okay? Currents entering point A are I4, okay? And then by the direction of the current, we can see that I2, I3, and I5 are all leaving point A. So in equation now, we can say that we have I1 plus, okay, so the summation, so I1 plus I2. Since I2 is leaving, so we have to denote it as negative, okay? So plus, again, since I3 is leaving, we have to denote that again as negative. Plus I4, since I4 is entering, so that's positive, and since I5 is also leaving, that is negative, okay? Or rearranging the formula now, we have I1 plus I2 minus I3 minus I1 plus I4 minus I2 minus I3 minus I5 is equal to 0. Okay? So, combining together those with the same signs, so we will be having I1 plus I4 is equal to I2 plus I3 plus I4. Or simply, incoming currents is equal to outgoing currents, like that. Okay? Okay, so looking at our next example here, we have here your I, okay, entering point 4, point A, and then looking at the values of the different currents, I1, I2, I3, and I4, and by looking at their directions, all of them are leaving point A. So therefore, we have I plus minus I1 plus minus I2 plus minus I3 plus minus I4 is equal to 0, or simply I is equal to I1 plus I2 plus I3 plus I4. Okay, so just like that, or simply the summation of your current is equal to 0. So that is the first law of Kirchhoff's current law. Okay, so we have the second law. Okay, so we call this as the Kirchhoff's mesh law, or the Kirchhoff's voltage law, or simply KVL. Okay, so what do we mean by KVL? We have here the algebraic sum of the products of currents and resistances in each of the conductors in any closed path or mesh, okay, in a network, plus the algebraic sum of the voltages sources in that path is equal to 0. Okay, so we have here the summation of IR. So IR is the voltage drop across each resistor, right? So if there is a current and there is a resistance, so the product of that is a voltage. So we call that IR plus EMF. Those are the sources that is present in your circuit. Okay, so the summation of those is equal to 0. So it should be noted that the algebraic sum is the sum which takes into the account the polarities of the voltage drops. Okay? So, originally, your resistors are non-polarized, or resistors have no polarity. But when a current passes through it, it can either have a voltage drop or a voltage uh, it usually has a voltage drop or a rise in potential or voltage rise. So it depends, okay? So therefore, once a current passes through a certain resistance, it develops, or it produces voltage already. So therefore, it will have a polarity. So resistors alone, it has no polarity, but the voltage drop across that resistor, it is the one with polarity. Okay? So we have here Kirchhoff's laws. Okay? So we have here your branch. So the basis of this law, if we start from a particular junction and go around the mesh till we come back to the starting point, then we must be at the same potential with which we started. Okay? So all sources of EMFs met on the way must necessarily be equal to the voltage drops in the resistance. Every voltage, okay, from the beginning is given its proper sign. So it's either positive or negative. Okay? So like this for example, so if this is our branch, so we have here your node, this is our node, and this is our loop. Okay? So for example, we will be calling this as in entering, and then we have here leaving. So the summation is I1 plus I2 plus I3. All of them is leaving, so that is equivalent to 0. Okay, so some currents in, okay, so that means no currents leaving. Okay, so -1, -1, -3 is equal to 0. So if it opposites in direction, if it is in opposite direction. Okay, so some voltages counterclockwise. We have here if this is plus or minus. So if we leave the loop here, you have, if we enter the loop, for example, you have positive, or if you leave the loop, you have negative. So it's either you're going to address that in a counterclockwise manner. Okay, so if this is your counterclockwise manner, you will start from V5. Okay, so counterclockwise manner. So this is positive V5. You have here positive V6. You have positive V7. You have positive V8 is equal to 0. If you're going to go on a clockwise manner, so that will become minus V5, minus V8, minus V7, and minus V6, like that. So it depends on you if you wanted to count at that as in the counterclockwise or in a clockwise manner. Okay, but you have to be very consistent. So how do we determine your voltage sign? Okay, so first, look at the sign of the battery or the source. So it is fixed. So every time you're given a battery or a source, there's a positive and a negative sign to that. Okay, and then sign of the IR drops. Okay, so how are you going to do the sign of the IR drops? So first, we have a rise and fall. Okay, the sign of the battery is independent of the direction of the current through the branch. So it's independent, although the direction of current can be taken from the direction of your battery or your source. Okay, but it is independent. It has its own polarity. So we say we have a rise in voltage. So why rise in voltage? Because we have from negative going to positive. So this is a rise in voltage or positive E. And then we have a fall in voltage. So what do we mean by a fall in voltage? So we have here from positive going to negative, or that is equivalent to negative E. So that is a fall in voltage. Okay? So how about in the voltage drop? So for example, we have here a resistance. Let us just look at the direction of the current. So when the current enters, where the current enters, it is positive. Where the current leaves, it is negative. Okay? So therefore, we have a fall in voltage. So why fall in voltage? Because this is positive going to the negative direction. Okay? So if the current flows in this manner, as I have mentioned a while ago, where your current enters, that is positive, and where your current leaves, that is negative. So if this is our motion, okay, this is a rise in voltage. So why rise in voltage? Because from negative going to positive, or we have a positive IR or rise in voltage, we have a negative IR or fall in voltage. Okay, so the polarity of your resistors here will depend on the direction of your current. Where the current enters, it is positive. Where the current leaves, that is negative. But it is independent on the motion or in the direction of the loop you are trying to create. So it's either clockwise or it is either counterclockwise. Okay? So we have here, consider this loop here. Okay? So this is the direction of travel, and then we have here different direction of currents. Okay? So at R1, we have here plus, where current enters, this is 1 plus, therefore this is negative. Okay? So I1 R2, I1 R1. So this is I1 R1, it is negative VE. This is what do you call this, typo error class. It should be R1. So I1 R1, so this is negative VE or fall in potential. So this is I2 R2, positive, negative going here. So therefore this is I2 R2 minus again. This is negative fall in potential. So we have here minus E2. So minus E2 is negative VE, fall in potential. Okay? We have here, this is the direction of your I3. So therefore it is positive here. This is negative here. So you have plus I3 R3. So that is a rise in potential. E1. So from negative to positive, that is rise in potential. And this is the direction of your current. So this is plus, this is minus. So again, minus I4 R4, that is fall in potential. Okay? So therefore, if we're going to rewrite that, all fall in potential is negative and all rise in potential is positive. So that will give us minus I1 R1, minus I2 R2, minus I3 R3. So we're just following this direction of travel, okay? So, and it is dependent, the direction in the resistors will be dependent on the direction of current. So, we have here minus I4 R4 minus E2 plus, I think we have something wrong here. It must be positive. So, this is positive I4 R4 minus E2 plus E1. Or, you have here I1 R1 plus I2 R2 R2 minus I3 R3 plus I4, only I3 R3. Only I3 R3 has positive. Okay, so I3 R3 positive, then plus I4 I4. So, that will give us equal to E1 minus E2. Okay, so this is typo error class. So, this must be positive I3 R3. Because this is positive, this is negative, and following this direction, we will leaving the positive side. So, this is rise in potential. So, only I3 R3 has a rise in potential. So, it's either negative sila or will make them positive, and ang matitirang negative is si I3. Or, this will become E1 minus E2. Okay? So, usually, we put all the EMFs together, we put all the sources together, and we put all IR drops together in the same side. But all in all, it must be equal to 0. The summation of the voltage drops and voltage rise must be equal to 0. Okay? So, how about the assumed direction of current? So, the important point is that once a particular direction has been assumed, so the initial assumption is safe. Okay, so the initial assumption is safe. It's up to you. Anyway, if it is wrong, all you have to do, all you can get is a negative answer. So if you got a negative answer, that means we have a wrong assumption. What you're going to do is just to reverse the direction. But the first assumption is all right. You can assume that. But okay, the important point is once a particular direction has already been assumed, the same should be used throughout the solution of your equation. Okay? So, we have here how to assume the proper direction of current. So, it's either clockwise or counterclockwise. If the assumed is not the actual direction, all you can get is an answer, a correct numerical answer with a minus sign. Okay? So, for EMFs, capacitance and inductance, they can store charges. Okay? So, we can have in EMFs when you use capacitors and inductors. So, this is also very important when we're trying to solve simultaneous equations. Okay, so if positive, then if your answer is positive, therefore your assumed direction is really uh, the actual direction. So don't be afraid to make an assumption. It's all right as long as the steps that you're following are correct. You can get the same numerical answer. So if you get it positive, therefore your assumption is correct. If you got it negative, you have the correct answer just with a wrong sign assumption. Okay? So let us try solving problems. So in here, we will be applying KVL. Okay? And then we're going to solve simultaneous equations. Okay, so for simultaneous equations, the number of unknowns must be equal to the number of equation. But anyway, this is just we can just create a single equation out of this. This is very simple, class, actually. So we'll just try to determine whether you understand the concept of voltage drops and voltage rise. Okay, so all we have to do is to as we have mentioned in our previous videos, okay, in an open circuit you can read a certain voltage there. Okay, so what is not present in an open circuit, it's the current, but you can read voltage across an open circuit. So in this case, we are asked to solve the voltage Vs across the open switch in the circuit. So all you have to do, class, is just to make a loop. Okay, so let's make a loop. You have there, we start with D, okay, at this point. So let's make a clockwise loop. Okay, so you can see you have negative 20, your loop left minus 20, and then you have minus 50, you have positive 30, so the longer line is the positive, the shorter line is the negative, and then you have plus Vs, okay, then you have plus 10. So, we have only one unknown. So, what is our unknown? Our unknown is Vs, and we have one equation. So, therefore, this problem can easily be solved. Okay, so, solving for Vs, leaving Vs on the one side of your equation, and then transferring all of the others on the other side of the equation. So, that will give us positive 20, plus 50, minus 30, minus 10. So, therefore, we have positive 30 volts. So what do we mean by positive 30 volts here, class? We got a positive answer. So that means the assumed direction of Vs, which is minus plus, it is correct. Okay? However, if that is wrong, let us say it becomes plus or minus, so therefore your Vs here will become minus. So if your Vs there is minus, so we will be transferring that to the other side. It will become negative 20, minus 50, plus 30, plus 10. So what we'll have there is what? Negative 30. So the negative 30 will only will signify that the assumed direction is wrong. So therefore, we will change the direction. Instead of plus minus, it will become minus plus, which is the original assumed direction. So therefore, this answer is, or this direction is correct. Okay? Okay, so let's go to our next example. So we have here, okay, So we have here, find the unknown voltage V1 in the circuit. So where is V1? V1 is the voltage across R1. Okay, so we don't know R1. So let us see what will be. So in order for us to know V1, we have to solve first for I, or the current flowing across R1. Okay, but if we're going to follow the loop, okay, let us say there are two unknowns. You have R1, you have R2. We don't know the current. So you might be wondering whether this is an example of a difficult type of problem. Actually, this is very simple, class. All you have to do is to move, okay, at the outside loop. Okay, so by doing that, we have here, okay, so example number 2, when current enters here, this becomes positive, and when it leaves here, this becomes negative. So we have there negative multiplied by the drop and the current. So this is 16, your 16 amperes multiplied by the 3 ohms resistor. So why do we have a negative sign here? Because your current passes here, so this will become positive, and this is negative. So our loop is clockwise, so it leaves excuse me, it leaves the loop at the negative side. So therefore we have minus 16 times 3. Okay, continuing, we have here the current enters here. This is positive. The current leaves this 2 here. So we have again minus there. So minus, current is 4 times 2 here. Okay? So continuing the path, you have positive 40 because the loop lives at positive 40. And then we have here minus V1. So we can go directly to V1. No need to solve for the I. Okay? So that is minus V1. Okay? So solving for V1, let us place V1 at the other side of the equation. So that will give us 40 minus this is 48 minus this is 8. And that will give us negative 16. Okay, so in this case, we have a positive sign. So what do we mean by a positive sign? So the positive sign there indicates that we have assumed the direction for R1 or for V1 wrong. Okay, so therefore, instead of minus and plus V1, the correct direction should be plus and minus V1. So it's all right. The numerical answer is correct. Okay, so the numerical answer is correct. Just the direction. So instead of minus plus, it should be plus and minus. Okay, so that is how KVL is being done. Okay, so let's have another problem. So we have here, using KCL, okay, so using KCL and Ohm's law, so combination of KCL and Ohm's law, find the magnitude and polarity of voltage V. So we didn't assume polarity for voltage V, so we need to know what will be the direction of the two currents, current sources. Okay, so we have two current sources here, 30 amperes, and we have here your current source, 8 amperes. So we can redraw and we can assume direction. Okay, so I will be showing you the solution. I have assumed the direction first. Okay, so I told you it is not a problem to assume the direction of your current. So it's all right, because if the direction is not the same or is wrong, all we will be getting is a negative answer. So if the answer is positive, therefore we have assumed the right direction. So I will be assuming this to be I1, so leaving node A. I will assume this as my I3, leaving node A, and I will assume this direction I2. entering node A. Okay? So, in this case, I will try to have, this is my direction. So, current will be entering here. So, this is plus and minus. Okay? Current is entering here. So, this is plus. Leaving here is minus. Current is entering here. So, this is plus. Leaving here, this is minus. Okay? So, since I will be using KCL, I will be concentrating more on the currents first. So, at node A, this is my node A, I have a leaving I1, okay? I have an entering 30 amperes. I have an entering I2. I have a leaving I3. And I have a leaving 8 amperes. Okay? So, what I have here is minus I1 plus 30 plus I2 minus I3 minus 8. So, this is now my, what do you call this? This is now my equation. So, rearranging, I have I1 minus I2 plus I3 is equal to 22. However, I have 3 unknowns and I only have one equation. So, I cannot really solve for I1, I2, and I3 yet. This is the time that I will be applying Ohm's law. Okay, so how will I solve for I1? So, since they are in parallel, that means my V here are constant. Okay, so my V here are constant. So, therefore, I1 is equal to V over 2, I3 is equal to V over 4, and I2 is equal to negative V over 6. So, why negative V over 6? Because based on my direction, this is minus plus. And this is plus minus. This is plus minus. But this is minus plus. So, therefore, I have there negative V. Okay? So, by substituting the values now, I1 is equal to V over 2 minus I2 is negative V over 6 plus I3 is V over 4, that is equal to 22. Okay? So, I have now one unknown and my unknown is V, which is equivalent to 24 volts. Now, I have a positive value for V. So, what does that mean? So, that means that I got the assumption right. That the value for here is minus, that the polarity for this is minus and plus V. Okay? So, find the magnitude and the polarity of V in the figure. Okay? So, that is how we're going to combine, so that is how you're going to combine Ohm's law with your Kirchhoff's laws. Okay? So, let us have another problem. So, we will be considering this problem, okay, the two battery circuits separately. Okay, so the voltage drops over different resistors can be found using Ohm's law again. So, we will combine this again with Ohm's law. Okay, so VCE, so where is VCE? So, this is VCE. So, the first is your C here and this one. So, VCE and this is AG. So, where is AG? This is your AG here, VAG. Okay? So, how are we going to make a loop there? So, how are you going to make a loop there, class? So, to solve for VCE, we are going to go from E, okay, E, F, G, H, B, and C. Okay, with respect to E. So, with respect to E, so that is E is negative with, C is negative with respect to E. Okay, based on these sources here. Okay, and for VGA, that is from G to A. wherein 30 is positive with respect to G. Okay? By combining this 20, this 10, and this 40. So we can assume that E is positive because 40 is greater than 10 and 20. And then we can say that this is positive because it is greater. So 20 is greater than 10 here. Okay? So if we're going to do that, let us look at the solution here. So for the 20 volts, okay, so for the 20 volts, that is A, B, C, and D. So your current there is 20 divided by the resistors there, that is 6 plus 5 plus 9. So for the 20 volts, the answer is 1 ampere. Okay? So for the 40 volts, we have two separate circuits there. It is 40 divided by the 3 resistors connected across the 40 volts voltage. So that is 8, that is 7, and that is 5. So that will give us 2 amperes. Okay? Now, to solve for VCE, you have negative 5, okay, times 2. So negative 5 times 2, this one, so negative 5, this entering positive. Okay, so negative 5 times 2, you have there plus 10. So from E. So if the direction is this one, negative to positive, so this is positive, negative. But we're going from E to C. So therefore plus, minus. So we have here negative 2 times 5. Then we have here plus 10. So the current here is, this is minus plus, so positive, negative. So we have here minus 5. Why minus 5? Because we have here 5 times 1. Okay? So therefore, minus 10 plus 10 minus 5, your VCE is negative 5. So what do we mean by negative 5? So negative is negative, C is negative with respect to E. So it should be VEC and not VCE, like that. So we just have to, because the first subscript usually signifies the positive terminal, and the second subscript the negative terminal. So in this case, since this is negative, so therefore the proper subscript must be VEC, because C here is negative with respect to E. So for VAG, okay, so we start from 7, so this is your G. So we have here plus and minus. So we have here plus 7 times 2 going to positive 10, okay, and then we go to A here. So this is plus and minus. So we have here again plus 6 times 1. So therefore, you have 14 plus 10 plus 6, that is 60 volts at 30 volts. So since this is positive, what does that mean? That means A is really positive with respect to G. So VAG is just correct. Okay? So this should be VEC, and this is really VAG. Okay? So that is just how we solve for this type of problem. Okay? And then, we have here another problem. So, we have 3 unknowns. Okay, so we need to determine the branch currents in the network when the value of each branch resistance are all 1 ohms. So all of the resistances here are 1 ohms. And then we have 3 unknown currents. So what are those 3 unknown currents? We don't know X, we don't know Y, and we don't know Z. Okay, so therefore, we really need to have 3 equations to solve for these 3 unknowns. So we just have to follow the circuit here. Okay, now, don't be afraid because, are we going to make use of delta to Y transformation because we have here a delta form? No, let us first try to solve it using a simple KCL, KVL, and Ohm's law. Okay? So we have here your solution. Let us first make our equations. Okay? So I will go to A, B, D, and L. So where is A, B, D, and L? So this is A, B, D, and A. So this is A, B, D, and A. So this one. So that is positive 5. So current will enter here. So it will leave here. So minus X. Okay. So Z here, it will enter here, minus here. So minus Z. Okay. And then your Y here, positive, negative. So we will leave at positive Y. It will enter here. So you have here plus Y. So you have X plus Y. X minus Y plus Z is equal to 5. So, 3 unknowns, still one equation, so we cannot solve this yet. So, let us just call that our first equation. Okay, so where are we going to get our second equation? So, let us go to BCDB. So, where is BCDB? So, BCDB. Okay, so BCDB. So, we have here our loop. So, you have there minus. This is your X minus Y. So, therefore, you have minus X minus Y. Look at the direction. So, you have plus 5. This is Y plus Z. So, you will be, and this is entering, this is leaving. So, therefore, you will leave at the positive terminal. So, you have plus Y plus Z. And then, we have here plus Z. Okay? So, that is equal to 0. So, simplifying this equation, so by distribution and by combining terms, we can have X minus Y minus 3Z is equal to 5. So still, we have 3 unknowns. We only have two equations up for now. So what do is we have to get one more equation. And where can we get it? We can have your equation this, C and A. Okay? A, D, C, and A. So we have here A, D, C, and A. So by having a loop there, you will be getting minus Y plus Z, plus 10. 10 is our source. Okay? Minus Y plus X is equal to 0. Combining those three now, okay, those equations now, we have X plus 3Y plus Z is equal to 10. Now, we have 3 equations with 3 unknowns. So, we can say now that we can solve these 3 equations simultaneously. Okay. Either using, by using either equation number 1 or equation number 2, we can look at this as X minus Y. Okay. So, either using either equations 1 and 2, both of equations 1 and 2 will give us a value of Z is equal to 0. Okay? So, substituting number 2, number 3 in either 1 or 2, so anyways there, okay, we can have X minus Y is equal to 5 and X plus 3Y is equal to 10. So, let us call this 4 and 5th equation. Okay, so, by using this 2, so this is just like algebra. Okay, we're solving na lang like this. So, X minus Y minus is equal to 5 and we have here X plus 3Y is equal to 10. So, by subtracting this, subtracting 3 to in either 1 or 2, we have here minus 4Y is equal to negative 5. Okay, so we can solve for Y. So, Y is equal to 5 over 4 amperes. Then, substituting that to our equation, that will give you X is equal to 25 over 4A. So, we know already Y and we know already X. We can then solve for the branch currents. So, what are the branch currents? So, branch currents at branch A and B is equal to branch B and C. Okay? Why? Because the currents flowing at A and B is just equal to X. Why? Because Z is equal to 0. So, therefore, it is equivalent to X, which is 25 over 4 amperes. Okay? So branch BD is equal to 0. Why? Because the current that flows across branch BD is Z, and we know that Z is equal to 0. Now, A and B is equal to D and C. Why? Because at A and D, the current flowing here is Y, and at B and Z, the current flowing is Y plus Z. However, Z is equal to 0. So, therefore, branch A and D is equal to branch D and C, which is equal to Y, which is equal to 5 over 4 amperes. Okay? And for C, E and A, so C, E, and A, that is equivalent to X plus Y. So, X is 5 over 4, and Y is 25 over 4. So, therefore, the current at CEA is equal to 15 over 2 amperes. So, the moment we have determined your X, Y, and Z, automatically, we can easily solve for each branch currents. All we have to do is to determine your X, Y, and Z. And if you have 3 unknowns, you should have 3 equations. Actually, you can have more equations there because you can even look outside, okay? But no need because we only have 3 unknowns and 3 equations may do. Okay? So, I want you to also to review some since we will be dealing with more equations, so I want you to review some mathematical ways in simultaneously solving equation. And one of that is what you call the Cramer's rule. Cramer's rule. So if you have time, kindly read the Cramer's rule because from this moment on, we can easily formulate equations. So by using KCL, KVL, by looping, forming an equation is now easy. No, but the problem really is on how to solve those equations. And I want you to have some advanced, some additional readings or review, okay? So with your math, with your algebra about Cramer's rule or the determinants like that. So that will help you. So I will be helping you in formulating equations, but these rules here, this mathematical topics here will help you in solving simultaneous equations. Okay? So I think that's it. Thank you for listening. Okay, so that is about KCL and KVL. So the next video is about other theorems that will help you solve problems or circuit analysis easier. Okay, so thank you for watching and have a nice day. Okay, bye.